Hi, everyone. This is the lecture for Physics 102, March 18th. Well, given the unusual circumstances and the fact that we've been out of class for a long time right now, what I decided to do is it's probably best that I just rewind and review all the material that we did after the last test. And so what I'm going to start with today is the stuff that'll be on the beginning of the stuff that'll be on the next test. Okay. I'll review it a bit quickly, but because we've gone over it already, but it's probably be best that I do that to try to avoid confusion as to where we're at in the course. So all of our material will be on freeskies.net. And so if you go to that our Moodle site and you just log in with the username password, the usual username password, and then navigate to our course like that. And you'll see that, the usual subjects that I have and then the links for it. But what I decided to do is at the very bottom of the course page, you'll see I have these online lecture notes, and there you can see the March 18th and the March 20th lecture notes. And basically these are PDFs of the notes that I would have given you in class. In fact, some of them are notes that I gave you in class, and I just refurbished them for the purposes of these lectures. So this is the lecture for March 18th. And if we click on that, what you should see is you'll get up a PDF of the notes. Okay, and so let me move this window here down here so that I don't cover over the PDF. All right, so what I'll lecture on today is basically the wave equation, and it's just a review. And then at the very end of the lecture, what I'll do is I'll show you a few questions, assignment questions that you can work on to practice the ideas that I'm going to lecture on today. Okay, and if you have any questions, you can ask those during the live stream. All right, so the wave equation is a bit of a challenge for students. It's probably the most difficult equation that we're going to be studying, but it's very rich and it's got a lot of information in it. It basically describes all the kinematics and dynamics of waves, and so it is worth looking at, even though I'm not going to fully derive it for you. Uh, so let's start. A wave is basically a collective phenomenon. It isn't just one object doing whatever motion that it does. It's actually a bunch of objects, or a collection of harmonic oscillators. You could think of, if you're thinking of a string, you can think of every point on the string as being an oscillator. And what does the oscillator do? What the oscillator, point on the string, it's going to oscillate in place, okay? But it doesn't oscillate in place in isolation. It's coupled to its neighbors, and coupling just means it influences its neighbors. So as this one point in the string starts to oscillate, it induces its neighboring points to start oscillating as well, and they induce the neighbors, which induce the neighbors, and that's what causes the wave phenomenon to propagate out. So you can imagine you have a string and you just grab one end of the string and you start to wiggle it. Well, it won't be long before the neighboring points of that string start to wiggle, and then those neighboring points start to wiggle, and those neighboring points start to wiggle, and then before you know it, you've got a wave traveling down the entire string. And so what equation could you possibly write that describes such a thing? And so that's what we're going to discuss today. And there's a couple of conclusions at the end, which are more of what I'll test you on than actually, deriving the wave equation, because I'm not actually going to derive it for you. It's a bit too demanding to do that, but I do want you to have an appreciation of what's in it. So before we jump into the wave equation, though, let's go to the simple harmonic oscillator, just one oscillator. And so this is last semester stuff, but we need to review it right now. So if you have a single mass, and this mass is, say, attached to a spring, and the mass wants to sit at an equilibrium point, it just sits there. But if you pull the mass away from that equilibrium point, the spring is going to want to restore it back to equilibrium. Okay, and so this is known as Hooke's law. Basically, if you have a force that wants to restore something back to equilibrium, which is proportional to how far you displaced it from equilibrium, you basically have Hooke's law. Okay, so you double how much you've pulled it, you get twice as much force. You triple how far you pulled it, you got 3 times as much force pulling back. Okay, so we've seen the Hooke's law several times now. It's F is equal to minus kx. The minus, because if you displace the mass to the left, the force is to the right, because it wants to pull it back to equilibrium. Okay, so F is equal to minus kx. That's Hooke's law. Now, if you apply Newton's second law to the force, you can write that as ma, and then divide both sides. You get A is equal to minus k over m times x. And k over m we can write as omega squared, and you'll see what omega squared is in just a bit. We know, because we did this before, that it's the angular frequency, but you're going to see it arise now in the context of the wave equation. So you get A is equal to minus omega squared x, and you wonder, well, what can I do with that? How does that at all describe my kinematics? And what you need to do is you need to write the acceleration as the second time derivative of the position. Okay, and so let me just scroll this up a bit. So there you have d2x over dt squared is equal to minus omega squared x. Okay, the equation in a box. And you can say that's the equation for the simple harmonic oscillator. It's the kinematics, all the kinematics for the simple harmonic oscillator comes out of that. And we saw that last semester, and the solution to it is very simple. It's basically a sinusoidal. You could either use a sine or a cosine, and we generally choose a cosine. And so you could say x, the position of that mass, as it's oscillating back and forth, the position of that mass is basically a cosine in time. Okay, and so there it is. There's the solution at the top of the page. And it's got a few components in it. I mean, it is a cosine, but there's this a in front, and a is the amplitude. And you remember that the amplitude is the maximum displacement from equilibrium as the thing oscillates back and forth. Omega is equal to minus k square root of k over m. We just saw that by definition, but now you can see why it's an angular frequency, because it's cosine omega t. And so by the time you've made one complete cycle, capital T is equal to capital T, period, omega times t, capital T, must have gone through a change from 0 to 2 pi, because the cosine is periodic in 2 pi, okay? And we'll actually see that a little bit later too. And then phi is the phase, okay? Now, we didn't have that last semester, but I thought I'd throw it in here because you're going to hear me talking about phase when it comes to waves every once in a while. But basically all it is like at what point, at t equals 0, what point in the cycle are you at? So last semester we just said, well, you know, it was at maximum displacement at t equals 0, and so phi was 0, but you could be anywhere in the cycle. And so phi basically says, well, where in the cycle do you want to start? Okay, not that important, but you know, you can add it in there. All right, now how does this relate to the wave equation? So I'm not going to derive the wave equation, rather I'm just going to give it to you, okay, and try to explain what its components are. Okay, so motivate why it's true rather than give you a mathematically rigorous definition. And there it is in the square box there. It's d2y by dt squared is equal to v squared d2y by dx squared. Okay, and what are all the pieces in there? Well, y is the hard thing to understand. Y is the displacement, okay? But the displacement of what? Since this is a wave, it's made up of infinitely many harmonic oscillators. So again, you can think of the string, okay? And every point on the string can be thought of as an oscillator. And so y can be thought of as the displacement of the oscillator, which is at position x. And so if you have a string here and you want to take a look at a particular oscillator, say an oscillator down here on the string, all you do is you say, well, what's the x value of that oscillator? So you say x is equal to 5. Okay, great. That's the oscillator, say at 5 meters. Okay, or x is equal to 3. Great. That's that point on the string, which is 3 meters from an x equals 0, wherever that might be, some reference point. Okay, and so x is basically a measurement along the string, somewhere along the wave. Okay, and y, once you've got a particular x, say x equals 5, you move to that point. Y is how far is that displaced at a given time. Okay, so you've got y depending on two things. Y will depend on where you are in the string, that is, which oscillator you're looking at. But y will also depend on the time, because at different times you'll have different displacements. Okay, and so y is a function of two variables. It's a function of x and it's a function of t. And that's one of the things that makes this equation very difficult, because you guys are okay with you know, second order derivatives like d2y by dt squared, and there's also d2y by dx squared. But it's kind of hard to get your head around the fact that there are two variables. And in my next slide, I'm gonna try to really nail that home. So there I have, y is the displacement of the oscillator at position x from equilibrium. Okay, so it's how far did the oscillator, which is at position x, how far did that oscillator displace from equilibrium? T is the time, okay, and v will turn out to be the velocity of the wave. And that'll come out because once I give you the solution to the wave equation, which, surprise, surprise, is a cosine, and you plug it back in and you solve it, you see that it solves, and then it just comes out that v has to be the speed at which the wave propagates. I'm actually not even going to do that because we did it in class, and I don't want to go into, I don't want you to lose the forest for the trees. I just want you to have this kind of overall picture of what this equation is doing. So let's take a look at this y as a function of x and t, so we understand that better. Okay, and so here what you see is you say no, y is a function of both x, and that is where you are along the medium. Medium is just the material that is sustaining the wave, okay? Or you can think of the medium as the collection of all the oscillators that make up the wave, okay? In this case, we're thinking of maybe a string, okay? So you can see there in my first graph, you've got y up, and then x is along the vertical axis, and sorry, x is the horizontal and y is the vertical axis. So you could say, all right, you know what? I want to take a look at an oscillator at x equals 1. Okay, to say the oscillator is at x equals 1 is to say that point on the string at x equals 1. And say at t equals 0, the oscillator at x equals 1 is displaced the distance y1. You can see it there moving up vertically, so y1 is positive. You could say also at t equals 0, that's like your snapshot in time. You could say, all right, I want to see where my oscillator is, or how much the displacement is of my oscillator at x equals 2. Well, that's a different oscillator, and it has a different displacement from equilibrium. Even though it's the same time, t equals 0, it's a different oscillator, the one at x2, and it has a displacement y2, which from the diagram you can tell is negative. Okay, so y will depend on where you are along the string, because where you are along the string is which oscillator you're talking about, and which oscillator you're talking about will determine how much it's displaced from equilibrium. But y isn't just a function of x. It's not just the displacement isn't just a function of which oscillator you're looking at. Each individual oscillator itself will change its displacement over time. So if you take a look at a later time, okay, so you can see in the graph below, the second graph, I've got there t is greater than 0. All I mean is just some later time. I don't care how much later it is. And you can see that the wave has moved a bit, okay? And now if you ask, look at that oscillator at x1, well, now its displacement y1 is different. This time it's negative. Okay, and you say, well, what about that oscillator at x2? Well, that oscillator at x2, that one's different. Before it was negative, now it's positive. y2 is positive in that diagram. And so you could see that the displacement will depend on which oscillator you're talking about, in other words, x, and at what time you're looking at it, because the oscillators will change their displacement from the equilibrium over time. Okay, and so it's actually a function of both of those. Okay, so now that we have that understanding of what y is, we can return to the wave equation and understand it. Okay, understand it a little bit better. So how does this wave equation get derived? Okay, without going into details, how do you derive it? Well, you can actually start off by looking at the left-hand side of both the harmonic oscillator equation and the wave equation. And if you take a look at the left-hand side of the oscillator equation, that was the first equation that we looked at that came out of Hooke's law, we had d2x by dt squared, where here x is the displacement. Okay, don't confuse x for the harmonic oscillator with x for the wave. X for the harmonic oscillator is the displacement of the mass from equilibrium. Okay, and so we have d2x by dt squared. Well, the second derivative in time is basically the rate of the rate at which a single oscillator's position changes with time. In other words, the acceleration. Okay, well, if you take a look at the left-hand side of the wave equation, it looks an awful lot like it. Okay, so you'll notice there that I wrote y of x. Okay, so d2 y of x over dt squared. Why did I write y of x? Because I'm saying look at point x. There's an oscillator at point x, and y is the displacement of that oscillator at point x. Okay, and so d2y by dt squared is the rate of the rate at which the oscillator at x, its displacement changes with time. In other words, it's the acceleration of that oscillator at x. Okay, and so it's very much analogous to the left-hand side of the simple harmonic oscillator. It's again the acceleration. Okay, but what's on the right-hand side? Okay, so I'm not going to scroll up. Oh no, what just happened? Okay, sorry about that, guys. Moving some windows around, I lost the capture. The right hand side of the simple harmonic oscillator, that was just x. Okay, and so there wasn't anything very interesting. But the right hand side of the wave equation, that's also a second order differential, but it's a second order differential with respect to x, not with respect to time. And so what does that mean? That's the coupling. Okay, the reason that's the coupling is because that's basically saying, how does this oscillator's displacement at x, how is it influenced by the displacement of the oscillators to the left and to the right of it? Okay, so the second order differential with respect to x is looking to the left and to the right of an oscillator at x. That's the coupling. Okay, and so basically you could think of it as the rate at which y changes with x, but you wonder, well, what does that mean? That's the curvature in the string. Okay, so the rate at which the rate of y changing with x, that is, well, let's just move to the next slide here. I think you can see it a little bit better. Okay, the rate at which the rate changes, that is the rate at which the slope changes, that's the curvature of the string. Where the curvature is the largest, let me just scroll that up a bit more. Okay, where the curvature is the largest, that's where you have the most influence from the neighbors. Okay, and so I've got take a look at the crest there. Okay, the diagram which is on the left. Okay, you see how I have crest there, and I've got this little circle around an X. I mean, I'm sort of saying picture that oscillator at that point right there. Okay, and it's right at the top of the crest, and it's feeling a tension from the string. It's feeling a tension to the left, and it's feeling a tension to the right. But notice that the tension to the left and the right, they're not opposite one another. There is a component to the left and there's a component to the right, and the left and right components will cancel. But both the tension on the left and the right, both of them have a downwards component. And so whereas the left and right components will cancel, the horizontal components will cancel. The vertical components don't, they combine. Okay, and so in this case where you have a lot of curvature to the string, you're going to have the tensions are going to tend to add. Okay, their horizontal components will cancel, but their vertical components will add. If you take a look at an area where there's low curvature in the string, okay, and this would be at a point between the middle of a crest and a trough, in other words, exactly where the string cuts across equilibrium, well, then the tension is pretty much cancels. Okay, and so in areas where there's low curvature, the tension cancels, and basically an oscillator doesn't feel any influence from its left or right. Okay, or it does, but they cancel out. Okay, the forces due to the oscillator to the left and the forces due to the oscillator to the right cancel out. Whereas in regions of high curvature, the influence from the forces for the oscillators to the left and to the right tend to pull it back down. And in fact, that's right, the crest would at that point start to come down. Okay, and so in the right hand side of the wave equation is kind of like a force. It's kind of like the force that's acting on a particular oscillator. And if you take a look with now all the insights that we have at the wave equation, you can see it there. The left hand side, that's like the acceleration, and the right hand side, that's like the force acting, and basically you have F equals ma. Okay, and so it's Newton's laws. Now I know that I'm kind of skipping over some factors, and there's a V in there, and you go, where's the mass in there, and so on. But I kind of buried all those details because I didn't want you to get lost in those details. But you could see that basically the wave equation is just Newton's second law, but it's Newton's second law applied to every single oscillator in the string, and each oscillator being coupled to its neighbor, so that if one oscillator moves, it exerts a force on its neighboring oscillator. And that coupling actually turns out to be the second order derivative, but with respect to x, not with respect to t. Okay, and so there it is. There's the wave equation. All right, not really a derivation, as I say in my notes. It's more like an appreciation of how that equation works. Okay, now I buried a lot of the details, so of course you're not going to see how v comes out, but v turns out to be a velocity, and if you go through the details for any particular type of wave, you can actually get the velocity of the waves in that particular medium. So for instance, the equation that you see there in a box, v is equal to the square root of t over mu, that's the velocity of waves in a string. Okay, and we did use this in class, and so what are the pieces in there? You could see there that T is the tension in the string, okay, and mu is the linear mass density, okay, because it's a string, it doesn't have any, it only has one dimension length, okay, and so you can only talk about a linear mass density. It doesn't make sense to talk about the density of the string. So if you have a string of length L and it has a mass m, the ratio m over L is its linear mass density, and we give that the symbol mu. Okay, but I didn't give you this in class, but I thought, why not at this point? You could do this analysis for other materials. For instance, if you do this for air, you get that V is equal to the square root of B over rho. And what's B? B is the bulk modulus, which we saw earlier in class. It's the compressibility of the air, okay, under forces, uniform forces, okay, and rho is the density of the air, and so you can see that there's a similar equation even for the speed of sound. All right, coming out of the bulk modulus of the air and the density of the air. And in fact, you can do this for all sorts of waves. Okay, you don't have to limit it to just waves on a string or waves in air. You could do this like on water waves on the surface, and all sorts of waves. You can even do it for electromagnetic waves, in which case you're looking at the permeability and the permittivity of free space. These are quantities which I'll talk about towards the very end of the course when I bring up electromagnetism, when we do electromagnetism. But generally speaking, the velocity of waves in a particular medium is equal to the square root of something that you might call the stiffness. That is how hard the material is to deform. Remember, those moduli were measures of how hard it was to deform a particular material. So it's the square root of that stiffness divided by some mass density. Okay, and all of that comes out of this proper analysis of the wave equation. Okay, that's enough of that equation, or how it comes about. Let's look at some conclusions that we can get out of it. And so the wave equation actually has infinitely many solutions, so we don't have to go through that theory at all. But the most obvious one is a cosine wave. Okay, but notice the cosine wave. You can see it there. Y of xt is equal to a cosine omega t minus kx. So it looks an awful lot like the harmonic oscillator, but the argument of the cosine doesn't just have the omega t, which is the oscillation in time. It has this kx, which is the variation spatially of the wave. Okay, and so omega, you can see the next equation, omega is equal to 2 pi over t. That's your angular frequency. We saw it with harmonic oscillators. It comes up again with waves. Okay, and capital T is the period. That is, it's the time for one complete cycle. All right, so if you were watching one particular point on the wave and say it's at a crest, that particular point, that particular oscillator would go through a trough and then would come back up to a crest. The time it takes for that one complete oscillation is capital T. Conversely, T is the time it takes from a crest. If a crest starts here and there's a crest here, the time it takes for the crest here to travel and then superimpose its neighboring crest over time. Okay, that is also a period. Okay, one complete cycle. All right, but that's omega. What is that K? So maybe I should just scroll back there, because you could see here there is omega t, but then there's minus kx. And you might wonder, what is this kx? Well, just like there's a periodicity in time, there's also a periodicity in space, okay? And k is a measure of that periodicity in space, and it's actually equal to 2 pi divided by the wavelength lambda, all right? And these 2 pi's are arising because the cosine has periodicity 2 pi, okay? And so you have to put that 2 pi somewhere, and we tend to put that 2 pi into omega for the angular frequency, and we put that 2 pi into k, which is the wave number, all right? It's called the wave number. Don't confuse k, the wave number, with k, the spring constant in harmonic oscillators. It's an unfortunate thing that both of these quantities are given the symbol k, lowercase k. But I don't know what to say. I mean, in the context, you can generally tell when you're talking about a spring constant or when you're talking about the wave number. Okay, and so oh, there it is. You've got basically periodicity in time and periodicity in space. So you can actually look and see or think about t and lambda as kind of being analogous to one another. Okay, so for the harmonic oscillator, you just had t, but for a wave, you have both t and lambda. T being the periodicity in time, and lambda being the periodicity in distance. Okay, that is, for the period, it's the time for one complete cycle. If you start at a crest, how long does it take for that point at the crest to go through a trough and then back to a crest again? That's one complete cycle. That's a time cycle. Okay, but if you're looking at the wave spatially, okay, and you got a crest here and a crest here, okay, so it repeats. You got a crest here, and then it goes through a trough into a crest, and then it does it again. So the periodicity spatially or in distance is basically lambda. So just like you have a periodicity in time, you have a periodicity in space, okay? Similarly, omega and k are analogous to one another, all right? So omega is the angular frequency. K is the equivalent of a frequency, but a spatial one, okay? So it's the reciprocal of the wavelength, all right? All right, now, I did do this in class, but I'm not going to do it here. If you take y as a function of x and t, equal to a cosine omega t minus kx, and you substitute it back into the wave equation, you would differentiate it twice with respect to x on one side, twice with respect to with respect to t on the other side, and then what you would get is an equation that looks like omega is equal to vk. And you go, well, what's that? What does that mean? Okay, well, I don't think it's that obvious writing it as in terms of omega and k. So if we take out omega, if we write omega in terms of the frequency and you write k in terms of lambda, then that equation actually looks like lambda f is equal to v. All right, and that one is a little bit more meaningful because now you can see that v comes out as an interpretation of the velocity of the wave. Why? Why is it obvious from, sorry, I should probably scroll too far. Why is it obvious from that equation that v has to be the velocity of the wave? That is the velocity at which crests travel by as the wave propagates. And if you write the frequency there, if you write the frequency as the period, okay, then you get that v is equal to lambda divided by t. But that's exactly what you mean by velocity, because lambda is the distance traveled in one cycle, and t is the time it takes to travel it. So if you have a crest here and a crest here, okay, so you've got these two crests, and you start at t equals 0, and you wait. When does this crest eventually get to where that other crest was? Okay, this crest is going to move too, but let's just keep a fixed point here, and we have a crest here, and we want to know how long does it take this crest to get to where its neighboring crest was. And so if you start at t equals 0, tick, 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 by the time you get to there, you've traveled a time capital T. So you travel the distance lambda in a time capital T, distance divided by time, that's a velocity. Okay, and so what you're getting is the velocity coming out of the wave equation as being a constant, actually, because lambda doesn't change in the solution, and the period doesn't change in the solution, and so basically you get that the velocity is a constant for the wave. All right. Now, not any one oscillator. One oscillator, is going to go up and down, so its velocity is always turning around. I mean, one moment it's moving up, and then the next moment it's moving down, and so on. But the wave phenomena itself, which is a collective phenomenon. If you got a crest here, that crest is going to move along at constant velocity. So there's one of the first conclusions that comes out of this wave equation, that basically you have a wave which will travel at a constant velocity. We're looking at the equation in the box there. A wave which travels at a constant velocity such that v is equal to lambda f. Okay. Um, And I guess here is, I forgot I had this slide in there, but this is basically an explanation of what I just said. So you can take a look at that equation there. You see that I have a crest at position 1 and a crest at position 2. And the distance between points 1 and 2 is lambda. And the question is, how long does it take the crest at position 1 to propagate to position 2? Okay. And the answer is time capital T. Okay. And so again, lambda divided by capital T is equal to V. All right. The other important equation, or sorry, important conclusion that comes out of the wave equation is this idea of superposition. And superposition is everywhere with waves, okay? So a lot of the phenomena that you're going to see in the next lecture, which are reflection, refraction, diffraction, interference, and so on, they're really superposition in disguise, okay? So you might wonder, how in the world is reflection really superposition, or and so on? And that gets into some very complicated mathematics known as Fourier analysis. So we don't have to go there, but basically, it's kind of like standing waves, where at the reflection point, the wave y, the displacement, has to go to 0, and then as soon as you impose that boundary condition, what winds up happening is you get the reflection that we'll discuss later. So everything really comes out of this this principle of superposition. And so what is it? Okay, it basically says that if you have two solutions to the wave equation, one of them call it y1 and the other one y2, well, then the sum of the two is also a solution of the wave equation. Okay, and that's so trivial. I mean, I did prove it in class, but it's just so trivial, because whenever you differentiate, differentiation simply distributes over addition. So if you have the second order time derivative of y1 plus y2, that's simply equal to d2y1 over dt squared plus d2y2 over dt squared. Okay, in other words, the differentiation just distributes over the addition. So if y1 is a solution and independently y2 is a solution, then y1 plus y2 is also a solution. So what does this mean? It just basically means that waves add. Okay, if you got two independent waves and they come together, they add. Okay, so it's kind of hard to show that with full waves. Okay, so all I did is I just had these two little pulses. You could think of them as just like two crests. Okay, so they're incomplete waves, and here are these two crests. You can see them on the top diagram. They're heading towards one another, and as they start to come together, they start to add up. Okay, and so they start to build up on one another's displacement. By the time they're right on top of one another, you can see in the middle diagram there, the third diagram, they're literally, the hump is twice as high. The displacement is twice as high. Why? Well, because you had one which had, say, a displacement of 1 unit, and another one which had a displacement of 1 unit. When they came together, they would just add up for 2 units, a displacement of 2 units. Okay, and then they start to come apart. Okay, and all this time they're traveling at a constant velocity. So then they start to come apart, and then they finally do come apart, and it's as if they hadn't even seen one another. They don't really disturb one another. They don't deform one another's shape or anything like that. They simply pass through one another. And as they're passing through one another, you say, well, what is the height of the string at that point? You just add the heights from the two independent waves together, and that gives you the total height. Okay, so there are two crests coming together. What would happen if you had a crest and a trough coming together? Okay, and that one's more interesting, because there they would actually subtract. Okay, so here you can see a top diagram. You have a crest on the left and a trough on the right, and they're coming together. They're going to collide. As they start to collide, they actually start to cancel one another. And then when they're right on top of one another, they totally cancel one another. All right. Now the energy's still there. It's not like the wave is gone. It's just that the displacement is 0, but there's still a velocity associated with that string at that point. Okay, and then they start to come apart, and eventually they come apart, and the the trough continues in the direction that the trough was traveling, the crest continues in the direction that the crest was traveling. Okay, and so this is known as superposition, and this is a simple little illustration of it. When we get to interference, this is going to come up again. Okay, because in interference, when we look at double slit interference, what we have is two wave sources. The two slits give rise to two wave sources, and as the two wave sources over propagate through one another, you're going to have regions where crests are meeting crests and troughs are meeting troughs, and they'll give you bigger crests and bigger troughs. This is known as constructive interference. And then there'll be other regions where crests are always meeting troughs and troughs are always meeting crests. And this is known as destructive interference, and you basically have a quiet area or a dark area if you're talking about light. Okay, and so superposition is very evident in that case, but it's there in all of the phenomena which we'll study in the next lecture. Okay, that's all for this one. It was just meant as a review. It's not quite a whole 1 hour, but this is good enough for now.